Hello everyone, welcome to the channel Statistica Hub. Now in this lecture we will see system of linear equations. System of linear equations. So let's see it. So this is basically the list of linear equations. Linear equations with n unknowns and they have the form like a11 x1 plus a12 x2 to a1n xn, that is equals to b1, and another equation which is a21 x1 plus a22 x2 to a2n xn, that is equals to b2, and similarly going on am1 x1 plus am2 x2 to amn xn, that is equals to bm. Okay, so this is my system of linear equations. Okay, and in this system aij's are the coefficient of unknown xi's and bi's are the constant. Okay, now let's just frame this system of linear equations into the matrix format. Okay, so for writing this system into the matrix format, we'll take out matrices like, just take out all the coefficient, write down all the coefficients of these unknown xi's in the matrix format like a11 a12 to a1n, similarly a21 a22 to a2n, going on am1 am2 to amn. Okay, and another matrix which is x1 x2 to xn, and that is equals to b1 b2 to bn, bn. Okay, so this is the format how we can write a system of linear equations into matrix format. Okay, so if you look at if you do the multiplication of these two matrices, okay, like what we do is we'll multiply this row into this column. Okay, and that is equals to b1, we'll got our first equation. Okay, and similarly if we multiply this row by the this column, then that is equals to b2. We have to just frame the equations here. Okay, and when we just frame the equation, we see that we got these equations. Okay, so that's how, that is the way that we can write the system of linear equations into this format, like that is actually ax is equals to b, where what is a is my coefficient matrix, and what is x is actually the vector of unknowns. Okay, and b is what, b is also a column vector, and x is also column vector. Okay, so let's just see it, that what are augmented matrix. Okay, augmented matrix. So augmented matrix are represented like this. Augmented matrix. Okay, that is equals to corresponding A matrix. What is my A matrix? That is A11, A12 to A1n, going on A1m to AMN. This is my A matrix. Okay, and with this A matrix, we have a column vector of B2, that is B1, B2 to Bm. Okay, then this whole matrix is my augmented matrix. Okay, and this is denoted like A comma B, where A is my coefficient matrix and B is the column vector. Okay, so this is the augmented matrix. Okay, now let's just see that if I have these two system of linear equations, that is ax equals to b. Okay, and another system is let's consider cx is equals to d. Okay, now these two systems of linear equations are said to be equivalent. these systems are said to be equivalent if augmented matrices. What are the augmented matrices of this? So if we consider this system, the augmented matrix for this is A comma B, and the augmented matrix for this system is C comma D. What are these augmented matrices of this corresponding system? Okay, so these systems are said to be equivalent if the augmented matrices, that is A comma B and C comma D, are row equivalent. Row equivalent. Okay, then these systems will be equivalent. Okay, now as we are talking about system of linear equation. Okay, so that is Ax equals to B. So basically the system of linear equations are of two types. Okay, that is we can have a homogeneous system of linear equation. Okay, and we can have a non-homogeneous equation. Okay, now the case of homogeneous equation, when did we have a homogeneous equation? When our b is equals to 0. In that case we have a homogeneous system of equation. That means our system of equation is Ax is equals to 0 in the homogeneous case. Okay, and in the non-homogeneous system of equation is the case when we have b which is not equals to 0. That means we have the system like Ax is equals to b here. Okay, for the non-homogeneous equation. So these are the two types of system of linear equations, that is homogeneous equation and another is non-homogeneous equation. Okay, now if we talk about the solution of this system of linear equations, that what are the types of the solutions? Okay, so system of linear equations. Okay, so talking about the solutions of these system, so the solution can be inconsistent and it can be consistent. Okay, by inconsistent we mean that the system has no solution. Okay, and in the consistent case we have a solution, and that solution can be unique solution. Okay, and we can have a infinite solution, infinite number of solution, infinite number of solution. Okay, so this is the type of the linear equation. We have two types of linear equation, and this is the solution cases in these linear equations. Okay, in the linear systems we have two types of solution, that is solution of the linear equations can be, solutions of the system is can be inconsistent and can be consistent, and in the consistent case it can be unique solution and it can be infinite number of solutions. Okay, now let's just see that what are degenerate degenerate linear equations. What are degenerate linear equations? Okay, so for a equation, for a linear equation to be degenerate, we should have all the coefficients of that equation to be 0. Okay, that means if all the coefficient of equation of linear equation are 0, then we have a degenerate linear equation. That means we have a system equation like 0x1 plus 0x2 to 0xn, and that is equals to b. Okay, so this is my degenerate linear equation. Okay, as it has all the coefficient that are equals to 0. Now let's consider that L is my system of linear equations. Okay, L is my system of linear equation. Here we have considered a single linear equation, a single linear equation which is degenerate. Okay, now let's just consider system of linear equation. Okay, now this system of linear equation, what does this degenerate linear equation cause effect to the system of the linear equation if the system has something as equation like degenerate in its system? Okay, So if this is the system of linear equation and it contains a degenerate linear equation, okay, so what do we do is that we have this ax is equals to b, and for finding the solutions of the unknown, we reduce our matrices to the echelon form, okay, and after reducing the echelon form, we got something like okay, this is the format, okay, and this is the unknowns, these are the corresponding unknowns, these are the corresponding value of the value of the constants of the b, okay, and this is the reduced form of the echelon form, echelon matrix, okay, and in the echelon form we have studied this. If we have a zero rows, if we have any zero row, then it should be at the bottom of the matrix, it should be at the bottom of the matrix, okay. So this is the case when we have a when we have a row which is zero in the matrix, okay, that is the coefficients of all these row are zero, okay. So in this case, if we multiply, if we form the equations, what we do here is for finding the constant, for finding the unknowns, we form the equations and we solve these equations, and when we form an equation corresponding to this row, we get something like this degenerate equation, as all the coefficients in this row are zero, okay. So the particular case here which arises, like if this is my b here, okay, this is, let's just consider the last element here is b, okay. So if my b is not equals to 0, okay, this is the case. If this b is not equals to 0, then the whole system L is no solution, has no solution, okay, because we have a some equation like which where b has some value, where b has some value, and all the coefficient corresponding to these are unknown, so we have a inconsistent solution, we have an inconsistent solution, that means it contains no solution, okay. And what is the case if b is equals to 0? And in that case we have that 0x1 0x2 to 0xn, and that is equals to 0, okay, and that is equals to 0. And in that case we can say that if we have something equation, if we have a linear equation like this, then every vector, let's just consider u, which is equals to k1 k2 to kn, this is what we are taking here, this as the, this is my solution set, this is actually the solution set we are talking about. So every vector in u in case power n, in case power n is a solution, is a solution, because this equation then satisfy all the vectors, because it has the coefficients as 0 and the corresponding result which is b is also 0, so it will satisfy all the vectors which are belong to this case power n is a solution of this system, okay. Or you can also say it like this, that uh, that this b is equals to 0, this that if we have b is equals to 0, then this linear equation, this particular linear equation in this system of linear equation, that this linear equation, it may be deleted, it may be deleted from system L without changing the solution set, okay. So the this equation, if we have b is equals to 0, then this equation will doesn't cause any effect to the solution set, and we can just delete this equation from our system of linear equations, okay. So these are what the system, the degenerate linear equations are, okay. Now we'll see the system of linear equations, system of two linear equations. Let's just see a particular case here of two linear equations in two unknowns. Okay, in two unknowns. Okay, so let's just consider two linear equations which have two unknowns, like a1x plus b1y is equals to c1, and a2x plus b2y is equals to c2, where x and y are my unknowns, and these are the two linear equations. Let's just consider this is L1 and this is L2. Okay, now what are the cases that we form? We form the cases like we can have this system has, if this system has exactly one solution, Okay, what will be the case that if this system has one solution? Okay, so we can have a one solution. This occurs when when the lines have distinct slopes and they intersect at the same point. Okay, so we form the lines by putting the in the two linear equation, and with two unknowns we give some value to x, and and we can find the value of y from that. Okay, so from that we will make a line. Okay, so for getting an exactly one solution, we will have the lines of these two linear equations, that these lines have, these are the, let's just consider that these are the lines L1 and L2 which formed after, which are, these are the lines which are forming with these two linear equations. Okay, and if these lines have distinct slope, distinct slopes, and they intersect at one point, they intersect at one point. Okay, and this is only possible when the coefficient of x and y, the corresponding coefficient of x and y are not proportional. That means a1 upon a2 is not equals to b1 upon b2. Okay, so we have these lines L1 and L2 which have distinct slopes and intersect at one point. That means we can have a line like just consider this is L2 and this is L1. Okay, so these two lines are intersecting at a one point and we get exactly one solution here. Okay, this is the case of one solution, one solution. Okay, now if you look this, so this is actually a1 b2 minus a2 b1, and that is not equals to 0. Okay, so if we form the matrix, if we form the matrix of coefficient by these two equations, we got a1 b1 a2 b2. Okay, then you can see that it is actually the determinant a1 b2 minus a2 b1, that is determinant of a is not equals to 0. Okay, that's what we mean to say here is. Okay, so it can have a one solution when the lines have distinct slopes and they intersect at one point. Okay, now the another case can be that if this system, if the system has no solution. Okay, when can the system has no solution? If the lines are parallel. Okay, if these two lines are parallel. Okay, and the lines have same slope but different y-intercepts. Okay, different y-intercepts but have same slopes, same slopes. We have done these concept of lines, I mean to say like intercept and same slope parallel lines in 11 12 too. Okay, so this is just the basic concept. So we have no solution when the lines are parallel and they have same slope but different y-intercept. So like it just, this is my L1 and this is line L2. Okay, so these lines are parallel. They have different y-intercepts. This is these are, they have different y-intercepts, but they have same slopes. Okay, this is the case of no solution. Okay, and in this case, my proportional method matrices, that is a1 upon a2 is equals to b1 upon b2. Okay, because they have same slopes, but that is not equals to c1 upon c2 because they have different y intercept. Okay, now the third possible case can be here is that if this system has infinite number of solution, infinite number of solution. Okay, so when can a system has two as infinite number of solution? When the two lines coincide, when these two lines L1 and L2 coincide, and coincide means this is my L1 and this is my L2. Okay, L1 and L2, in this case we have infinite number of solution, number of solution when the lines coincide, and you can see that if the two lines coincide, they have same slopes, they have same slopes and same y-intercept, same y-intercept. Okay, in that case the condition is like a1 upon a2 is equals to b1 upon b2, and that is equals to c1 upon c2. Okay, so these are the possible cases where we have taken the generalization of the two linear equations and two unknowns. Okay, these are the possible cases that can be formed here in this case. Okay, now we will see, take this into the further step. Okay, so what are the possible case when we have three linear equations in three unknowns? Okay, when we have three linear equations and that have three unknowns. Okay, let's just consider any of the three equations, and these three, we are taking non-degenerate linear equations. Point to be noted, we are taking non-degenerate equations in three unknowns. Okay, and the lines, they don't form a line. The three linear equations with three unknowns, they will form a plane. Okay, and the planes corresponding to these three equations we will have, let's just consider h1, h2, h3. These are my three planes with these three equations. Okay, now let's just see the cases here, that if this system has a unique solution. Okay, so they will have a unique solution if the three planes intersect exactly at one point. Okay, if these h1, h2, h3 intersect at exactly one point. Okay, let's just consider this is first plane, which is h1, and this is another plane, which is h2, and this is another plane. Oh, and this is the point at which these h2 plane and this is h3 plane. Okay, and this is the point at which these planes intersect. Okay, it's very hard to show this in the 2D, but let's just consider it like this. Okay, so this is the point where these three planes are intersecting. Okay, then can we have a unique solution in the three linear equations with three unknowns. Okay, and the second possible case is that these system has no solution. Okay, so they will have a no solution when the planes may intersect pairwise. Okay, uh, planes intersect intersect pairwise, but with no common point. They didn't intersect any common point, with no common point, or you can say that maybe two planes are parallel. Okay, any of the two planes are parallel. Parallel. Okay, in this case we will have no solution. So the condition for the no solutions is like planes intersect pairwise, and but with no common point, they didn't intersect at any common point, and the two planes are parallel. Let's just you can see it like this. This is my first plane, which is h1, and this is another plane, which is h2. These planes are parallel to each other, and the third plane, which is going like this. Okay, this is h3. Okay, so this is the case of no solution, and you can uh, see it like this, that let's just see, this is h1 and this is h2. Now these two planes are intersecting each other, but the third plane, let's say, which is going like this. Okay, this is not intersecting, these are not intersecting. Okay, so the third plane is here, and the two planes corresponding, which is h1 and h2, are intersecting each other. Okay, okay, so this is the case of unique solution and no solution in the three linear equation with three unknowns. Let's just see the third case. Let's just write it down here, which is of infinite number of solution. Infinite number of solution. So we will have an infinite number of solution when the three planes may intersect in a line, or they may coincide. Okay, they can coincide, or uh, the three planes may intersect in a line. Intersect in a line. Okay, the case formed here is like these are the planes h1, h2, h3 which are coinciding, h1, h2, h3. Okay, these planes are coinciding. This is the case of coinciding. And when we talk about the intersect, that they intersect in a line like uh, like this, that this is my h1, okay, and this is h2, and this is h3. Let's just take it here. Okay, so this is the case when they are intersecting in a line. Okay, in this case we have actually a one free variable. Okay, when we say that they intersect in a line, the three planes may intersect in a line, that means we are talking that they contain a free variable. Free variable. Okay, so this is how we can frame the we can see the linear equations into the geometrical way, that when we talk about the two linear equations and two unknowns, these are the possible cases of the one solution, no solution, and infinite number of solutions. And we have also seen the solution three linear system, three linear equations with three unknowns, and the corresponding geometrical representation of these unique solution, no solution, and infinite number of solution. Okay, okay, now let's do one more thing, okay, which is example. Okay, so let's just do that. Let's just consider a system of linear equation like x1 plus x2 minus 2x3 plus 4x4 that is equals to 5, 2x1 plus 2x2 minus 3x3 plus x4 that is equals to 3. Another is 3x1 plus 3x2 minus 4x3 minus 2x4, and that is equals to 1. Okay, so let's just frame these equation into the augmented matrix. For solving purpose, we frame this system of linear equations into the augmented matrix, like we can write them down like 1 2 3, 1 2 3, minus 2 minus 3 minus 4, 4 1 2, and the B matrix which is 5 3 1. Okay, now let's just apply the operations and reduce this matrix to its canonical form. Okay, so for applying the operation, we'll apply in R2 R2 minus 2 R1, and in R3 we will apply R3 minus 3 R1. Okay, and this will give us 1 1 minus 2 4 5, and this is 2 minus 2 0 0, and this will be 1 1, and this will be 8 minus 7, and this 5 10 minus 7. Okay, and the another is 0 0 6, and this is 6. Okay, 2 minus 14 minus 14, and 15 minus 14. Okay, okay, now let's apply another operation which is we'll apply on R3 R3 minus 2 R2, and in R1 which is R1 R in R1 we will apply R1 minus R1 plus 2 R2. Okay, so after these operation we will get 1 1, and this will be 1 minus 2 plus 2, this will be 0, and 4 minus 7, and this is minus 10, this is minus of 9. Okay, and R2 will remain same, that is 0 0 1 minus 7 minus 7, and the last one is 0 0 0 0 0. Okay, so I got my canonical form here. This is my, we are reducing this matrix A to the canonical form, whole matrix actually, we are reducing this whole to the canonical form. Okay, now if we frame the equation here, okay, the corresponding equations are x1 plus x2 minus of 10 x4 is equals to minus 9. Okay, this is b1 actually. Okay, we have seen this in the augmented, that augmented is basically a comma b. Okay, and the another equation is x3 minus 7x4 is equals to minus of 7. Okay, how am I writing this? So that is actually we write this equation into x equals to b format. So what is a? A is 1 2 3 1 2 3 minus 2 minus 3 minus 4 4 1 2, and x is x1 x2 x3 x4 x4. Okay, and that is equals to 5 3 1. Okay, so we are, after reducing this matrix, we are multiplying with this unknowns. Okay, and that is equals to, that is bi's, that bi's. Okay, we have applied this, we have used the augmented matrix for the simplification purpose. Okay, so I got these two equations here. Okay, now if you will see that x1 and x1 and x3 are pivot variables because they have pivot elements, that is x1 and x3. Okay, x1 and x3 are pivot variables because they have pivot elements. Okay, and x2 and x4, these are free variables. These are free variables. Okay, so we will find the value of x1 and x3 as these are pivot variables in the terms of x2 and x4, and that is equals to x3 is equals to minus of 7 plus 7x4. Okay, and x1 is equals to minus 9 minus x2 plus 10x4. Okay, so this is how we can find the solution of a system of linear equation by the use of augmented matrix. Okay, now there is a very important thing to show. That's why I have taken this example, that if you look this, that I have this matrix M, which is my augmented matrix. Okay, and that is actually equals to a comma b. Okay, and it has, let's just consider that general case, let's just consider the general case that this augmented matrix which is a comma b, and that has n unknowns. Okay, then the system has a solution if rank of A is equals to rank of M. That means the rank of this A matrix is equals to the rank of the augmented matrix. Then in this case, the system has a solution. Okay, and if we have rank of A that is equals to rank of M, and that is equals to N, that means the number of unknowns that we have. Okay, then in this case we have a unique solution. In this case we have a unique solution. Now let's just look at example. So in this case we have rank of this matrix A. What is the rank here? The rank of this matrix is 2. Okay, and if you look in the this is my A. Okay, and if you if you look into the rank of the augmented matrix, what is the rank of this whole matrix? The rank of this whole matrix is also 2. So rank of A is equals to rank of M. Okay, so it has a solution, that is this x1 and x3, but this solution is not unique. Okay, because we have free variables in that case. Okay, so this is the result that we have for the augmented matrices for a system. Okay, now there is another thing which is a system of linear equations and linear combinations of vectors. Okay, this is very important in the vector format too, and for finding the linear combination in an easy way. Okay, by the use of orthogonal property. Okay, by the use of dot product of orthogonal. Okay, and we will do homogeneous system of linear equation, non-homogeneous system of linear equations, that too in the next lectures. So let's just meet them in another lecture. Bye. Thank you.